we have already shown that recurrence, transients are class properties, and also period is a class invariant in the sense that if I has period D, then any element that belongs to the communication class of I will also have period D. Our next topic is what is called the canonical decomposition. Now, what is that? The canonical decomposition is essentially the following. So we know that recurrence, transients are class properties, so therefore each communication class is either recurrent or transient. Right? In the sense that for any communication, for each communication class, either all states are recurrent or all states are transient. So in these two cases, the communication class would be called recurrent or transient. Now what we will show, and this is going to be a very important step, we'll actually not complete the proof of this step today. We'll show that the recurrent classes are closed. So if you have a communication class such that one and hence all states are recurrent, then the class has to be closed. So closed meaning once the Markov chain goes into that class, it cannot go out of that class. Now what will that mean? So this will mean that the state space can be expressed as union of sets T in C1, C2 and so on, such that T consists of all transient states and then C1, C2 etc. are closed recurrent classes. Of course disjoint also. Note that T may not be one communication class. It may be union of a bunch of transient classes. But the point is that recurrent classes are closed and therefore we'll be able to write it as T, which has all the transient states, and then the rest would be communication classes which are closed. This is called canonical decomposition. This decomposition of S into such states. Now let's quickly recall what is a closed set. Remember that closed sets are essentially sets C such that a Markov chain starting in C can never leave C. Okay? So the precise definition was this. So basically, if you start from a state in C, then you would never leave C, you never hit C complement, or you never leave C in finite time. So in other words, the first hitting time of C complement is going to be infinite with probability 1, starting from a state in C. Then the way we check whether a set C is closed or not was C subset of S is closed if and only if Pij would be 0 whenever I is from C and J is from C complement. So in other words, if you take one state from C and one state which is not in C, the probability, the transition probability from I to J is going to be 0. So this is the criteria for checking C is closed. Now this criteria, along with canonical decomposition, will immediately give us a very important corollary. Namely, by rearranging the states in S, it is always possible to write the transition matrix P as this. So essentially, this will be like a partition matrix such that the first part would be, the first partition here would be a diagonal block matrix, and then the last part would be not necessarily, there may not be enough zeros there. So the point is there'll be a lot of zeros in the first part of this matrix. And this will come from the recurrent states. And this part will come from the transient states. Okay, so let's quickly prove this corollary. So this is more like a corollary of the canonical decomposition with the help of this proposition. Okay? So how do you prove this? It's actually very easy. You just use the canonical decomposition. Now what you do is you rearrange the states in such a way that the states in C1, the first recurrent class comes first. If the states in C1 should come first, then the states in C2 and so on. So when you exhaust all the recurrent classes, then finally you put the states in T. So if you do that, then because of the canonical decomposition and also the fact that from closed set you can never leave, closed classes in this case, you can never leave, the Markov chain can never leave a closed class, it will follow that P would look like this. So clearly then, this part corresponds to the the I should be from the transient state. So the state you're starting from, the Markov chain starting, is from the transient state. And from transient state, you can always go to the recurrent state. So that's why this may not be 0. But the point is, from recurrent classes, you'll never be able to go to a transient class. And therefore, this partition matrix is going to be a 0 matrix. All of these matrices will be 0 matrices. So the only possible transition possible is between recurrent states that are in the same class. If two recurrent states are not in the same class, they are not going to communicate at all. So therefore, these are all going to be 0. So all the off-diagonal block matrices in the first part here are going to be 0. Only non-zero matrices are the diagonal block matrices in this part. And that's because the recurrent classes are closed.